Moving into chapter 12, section 2 here, we are going to keep exploring the ideas of limits. We're going to do some tricks to find limits that are difficult. All of this is great calculus practice here. Now, this first section, what we're going to see is that you could actually break limits up. I'm going to mention each of these here. This is what this section is. It isn't all that helpful here. It will have more application in a full calculus course, but we'll see that it could be done. Okay, so this is really introductory, and I don't think it's particularly all that valuable on the examples that we have. Maybe there's some in the worksheets that are a little harder, but anyway, here's the point. Let's talk through these really quickly here. We're approaching the limit. What if you're approaching the limit of a constant? Well, it doesn't matter. So if you drew a line, this is the line y equals 2. Well, it doesn't matter what your value of x is. You're just always going to get that constant. So this is kind of obvious. You're always going to get 2 here no matter where you go. That line is always giving you a value of 2. So the limit of a constant is just the constant. Now, what they're saying here is that if we have a function, suppose 5x, that constant in the front, so really we could think of this as 5 times x, and the 5 doesn't really have anything to do with the actual limit part of it. It's the x that has the issue. So we could literally separate that. We could just pull that constant out front and then just find the value of the limit of x and then multiply our answers. Again, not super helpful at this point, but it could be done. Now, what if we were adding two different functions together? Think of two things being added together, x plus x squared perhaps. Well, we could separate them, and we could find the two individual limits, and then just find those two answers and add them together. That would be true. Works the same for subtraction. Suppose we had x squared minus x. We could find the limit of x squared, find the limit of x, and subtract those two. Again, it works for products as well. So we could separate if it was x times x squared, which again, I don't know why you would do this, but maybe x times the square root of x might be an easier one to see. We could separate these. We could find the limit of x, find the limit of the square root of x, and multiply those answers. Okay, hang with me, just a few more of them. This is going to be proved valuable in calculus. If you have a quotient, you could find the limit of the numerator and find the limit of the denominator, and then your limit for the original one is the two limits over top of each other. That's going to be helpful. And then exponents here, you can actually just find the limit of the function and then take it to that exponent. So suppose this was x minus 2 to the fifth. We could just find the limit of x minus 2 and then take it to that fifth power. Again, we're going to be a little short on application here without diving into a full calculus course, but it can be done. Same thing can happen with a root. You could just find the limit of what's inside of there, but that's kind of obvious because if we had this, can't that just be written as x minus 2 to the 1/2? So that same exponent principle should be true. And then polynomials we saw. Polynomials don't break anywhere. They don't have any issues. So this is just saying if you add 4x to the third plus 2x squared minus 5, that's a polynomial. Just put in a, just put in the limit you want and just crunch it, and there's nothing else to it. Okay, so we've already seen when we have this polynomial here, this line, it doesn't have any breaks. So we could simply put 3 in here and we could find the limit. So again, these illustrations aren't going to make a whole lot of sense because of our ability to do that. But what they wanted us to see is we could break this into these principles we just saw. We have the sum of two different functions, so we could make that two different limits. And we have a constant being multiplied by, the real function here is the x, so we could pull that multiplicate that constant out to the front. So we were multiplying by a constant, so we could just put him out front. Now, we could find these individual limits and then just follow the principles. The limit as x approaches 3 for this is just 3. 2 times 3 gets me 6. The limit of a constant is 5. So we're using the principles, but on this one, we didn't really need to do that. All we had to do is 2 times 3 plus 5 because it doesn't break anywhere, so it's not going to have any issues. We get 11. But we're showing here that these principles do hold true. You get the same thing. Okay, so try this on your own. Again, this is a little tiresome because we just could put in negative 12 and we could find our limit. But so we're going to break this though into individual pieces. I'm going to jump ahead. I'm not going to show all the steps here. So this first one plus, so I just broke this down. They're just trying to show us these principles in action. So I've broken it down. The negative 2 that's being multiplied by x can move to the front. I split this up into two separate limits. And I'm going to get the same thing, though, if I had just plugged it in. That's fine. The limit of x as it approaches negative 12 is just negative 12. The limit of a constant is just a constant. So I'm going to get 24 plus 2 here. I'm going to get 26, which is the same if I would have just plugged it in. But these principles hold. Okay, now I think they're doing the same thing here, but this is still just a polynomial. I could just put 3 in and I would be done, but we can separate that. We could pull the constant out front and then take the limit of this x squared portion. So the limit of this x squared portion is 3 squared is 9 times 5, 45. So again, nothing revolutionary here. We can turn this into two separate limits. We don't really need to, but we can. So we could think of this a couple different ways, but I'm going to think of it like this, as subtracting the two of them. Okay, so 4, isn't 4 to the third power? Oops. That's what I thought. Okay, so this gets me 64. If I put 4 in here, take it to the third power, minus the limit of this. This limit doesn't change. It's no matter where you approach, it's still just 5. And so we get 59. Okay, now I don't know if they're actually going to break this down. So again, if I had this polynomial like this, I wanted the limit. Polynomials don't have any problems. They're not going to break anywhere. I would just put 5 in and evaluate this. But they're going to show this the long way. They've separated all the individual terms. They brought out those coefficients out to the front and did them individually, but we didn't have to do that. But again, showing the principles. So if you want to stop this and do this, I think you're going to have no trouble, so I'm just going to do this. The hardest part is going to be reading my handwriting, I think. Okay, I've separated it. Maybe a better question would be, say, break this up into individual limits, because evaluating it's pretty simple. So I would be putting negative 1 into the fourth here, and get 1. So I'm just going to do this. So if I had negative 1 to the third power, that's going to give me a negative 1. That's going to make that plus 4, because I got a negative 1 out of this, a negative 4 there, plus 4. This is always just going to be 5 no matter what I do. And that's going to give me 10. Okay, so what they want to show us here, again, just putting these principles in action. Again, I think a better question would be, don't evaluate, but use the principles of limits to rearrange this would be a better question. So what we saw with exponents is we could just take the limit of everything but the exponent, and then get that answer, and then take it to the fifth power. The exponents don't have anything to do with it, is essentially what we're saying. So I could just find the limit of this, and then take it to the fifth power. So they did that. You get 7 when you just do the limit of this part, and then you take it to the fifth power, and you get this. Okay, same idea here. We're going to take the limit of 10x plus 36 as x approaches negative 4. We're going to find that limit, and then we're going to cube it. So if you put negative 4 in here, this doesn't have any issues to break, so this is going to get me negative 40 plus 36. It's going to give me negative 4, and then you're going to take that answer and take it to the third power. So we saw 4 to the third is 64, but with the negative in front, it's going to make it negative 64. Okay, again, the principles are important. None of the examples here really warrant the need for those principles, but again, to see the ideas that we could separate these limits into some baser pieces will be helpful when you move into calculus.